So this is lecture 10 on Hausdorff spaces. So this is part of a bigger story about how to classify topological spaces. So the criteria of Hausdorff is a very famous one of the first interesting criteria to describe a topological space. So let's get to it. So a topological space is called Hausdorff, or T2 space, if any two distinct points admit disjoint neighborhoods. So I'm going to ignore this definition and just work in it in terms of open sets. I much prefer to think in open sets. Equivalently, a space is Hausdorff if given x and y and x, with x not equal to y, we may provide u and v open with x an element of u and y an element of v, and u and v are disjoint. All right, so here's a picture. So you got your x, you got your y, you can find your u and your v such that these guys, they don't intersect. So you can separate, you like to say this, we can separate points x and y with open sets. All right, this is Hausdorff. So some people sometimes do work in spaces which are not Hausdorff, and that leads to certain advantages and certain disadvantages. But anyway, so example one, if you take a set and give it the trivial topology, and if you got two or more points, then you can rightly see that the space is not Hausdorff because you don't have any open sets to separate the two points, right? That's the thing. If you want to contain either of the points, you need to use x, but that's all you got. So, yep. I think it's not hard to come up with finite spaces which are not Hausdorff, and you can kind of extend this story to if you want to think about a space with 4 points. It wouldn't be hard to come up with a topology on a space with 4 points, which was not Hausdorff, I think. All right. On the other hand, if you have a metric space and you look at the metric topology on X, that is Hausdorff. Let's see why. So, I mean, if you want to think about that picture up there and think of this as a metric space, you can kind of already see why, right? If you just take the distance from X to Y, whatever that is, and if you use a ball of radius, less than half of that distance, then it's going to work, right? I mean, you can just kind of geometrically anticipate the proof down here. So let's look at it. So you got a metric space. Pick a pair of points that have non-zero distance between them. This is just a fancy way of saying x is not equal to y in a metric space, right? So you got x not equal to y. The distance is positive. You can pick any r to be less than half the distance, and then you can argue that the intersection of the ball around of radius r centered at x and the ball of radius r centered at y is empty. Towards a contradiction, suppose otherwise. Suppose that there was a z in the intersection of these two balls. Then if you look at the triangle inequality, you got the distance from x to y is less than or equal to the distance from x to z plus the distance from z to y. But this is less than r and that's less than r, so this is less than 2r. But remember, 2r is less than the distance from x to y, right up here, multiplied by 2, right? And oops, we've got the distance from x to y is less than the distance to x to y. No, you can't do that, right? 5 is not less than 5. Oops. So contradiction, no such z exists. And there you have it. Any metric space is Hausdorff. All right. These are not one-to-one. There exist examples of Hausdorff spaces which are not metrizable. Such examples are not that easy to come by, though, because, well, I looked a little bit, and it doesn't seem like they're easy examples. But if you can look, and there are examples. But anyway, so I will follow Manetti's lead there and just say that they exist, but I'm not going to give you an example. But anyway, in a Hausdorff space, finite subsets are closed. This is a really nice lemma, right? Very useful. So many of our examples are Hausdorff spaces, so it's very comforting to know that in an arbitrary Hausdorff space, if you've got a finite set, it's closed. Pretty cool. Here's how it goes. So it suffices to show that singletons are closed, since if you could get that the singletons are closed, any finite set is a union of singletons, and a finite union of singletons at that. So finite union of closed sets, of course, is closed once more. So it suffices to show that the singleton's closed. Let's do that. X be Hausdorff. Suppose X is an element of X. Let Y be an element of the complement of X by the singleton X. So since since X is Hausdorff and X and Y are distinct, we know that there exists U and V open with X contained in U and Y contained in V, and their U and V are disjoint. But what does that mean? That means that notice that implies that X is not an element of V. Right? If X was an element of V, then the intersection would contain X, and we know that's not the case. So X is not an element of V, which then means that V is actually an element of X complement the singleton, which is wonderful, because then that shows that around an arbitrary point Y in this complement, you have an open set contained in the set, which means that an arbitrary point in here is interior, which is to say that this is an open set, right? And if that's open, that means that the singleton is closed, and so the lemma goes. So that's nice. Next proposition. Here we go. Subspaces and products of Hausdorff spaces are Hausdorff. Suppose X is Hausdorff. Let Y be a subspace. Let X and Y be distinct points in the subspace. Again, since X is Hausdorff, there exists U and V subsets of X with X and U and Y and V, and U intersect V empty, right? And maybe I should draw a picture of this one, actually. I should have left myself. I should have just drawn this picture, and I regret I regret my choices in terms of writing here. So like here is X, right? And that's X. Let's say that's X, right? And let's make Y like, I don't know. I guess I make it brown. So I'll make Y like this, right? Okay. There's Y. And you got these 2 points, right? You got your X and you got your Y, right? Now, what was said is that X is Hausdorff, right? So you get open sets around X, you know, and an open set around Y, and these 2 open sets are disjoint, right? But they're subsets of X. They don't have to fit inside Y. But it's easy enough to fix that, right? All you do is you take your U, which I've drawn to be blue, and you take your V, which I made red there, yeah, and you take those and intersect them with Y, and lo and behold, you've got 2 open sets in the subspace topology, which are disjoint and respectively contain X and Y. Consequently, that means that we took an arbitrary points in the subspace and showed that you can separate them with open sets in the subspace, which is to say that Y is in fact Hausdorff. So that's cool. And to show that the product is Hausdorff, here's the argument down here in black. Let's see here. So you got X and Y are Hausdorff with distinct points, X comma Y, Z comma W, and the Cartesian product of X and Y. Without loss of generality, we'll assume that X is not equal to Z. If you understand this argument, it's pretty easy to see that you can make a similar argument if like Y was not equal to W, right? But anyway, see, because if X is equal to Z, then you can't have also Y is equal to W, because then these pairs would be equal. So if X is equal to Z, that forces Y to be not equal to W, which then there's a similar argument to what I'm about to give. So anyway, since X is Hausdorff, you can find disjoint open U, V, and X such that X is an element of U, Z is an element of V, and notice that X comma Y is in U cross Y, Z comma W is in V cross Y. These are both open sets in the product topology, and they intersect to just give you U cross V cross Y. U intersect V cross Y, but U intersect V was empty because we used the Hausdorff-ness. Hausdorff-ness, I don't think it's really the word, but anyway, we know that UV is empty, and the empty set crossed with Y is the empty set again, and so there we go. We have shown that the product of Hausdorff spaces is Hausdorff, at least for 2. And of course that can be extended inductively to N, right? But we don't go that direction here in this lecture. I'm just making a comment. You could extend that to 3 or 4 N things, right? Wouldn't be a big deal. Topological space is Hausdorff if and only if the diagonal is closed in the product. Now here's something that is really, this trick of the diagonal is something maybe you may or have not, I'm not sure if you've seen this before or not. I can't remember in my courses that I've taught you if this has come up or not. Using the diagonal is a sneaky move, and here's how it goes. So the diagonal is the pairs x comma x such that they're equal, basically. That's the diagonal in x cross x. Now suppose x is Hausdorff. Let x comma y be in the complement of x cross x by the diagonal. That is to say that x is not equal to y. And so there exists open u and v with x and u and y and v, and u and v are disjoint. Consequently, x comma y is an element of u cross v, which is, by the way, a subset of the complement of the Cartesian product of x with itself and its diagonal. So we just showed that there is an open set containing an arbitrary point in this complement, which is to say that this is an open set, since each point is interior, and if that's open, that means that the diagonal is closed, which is what one direction we're trying to prove. Oh, I'm sorry, I seem to have brought one direction into this. I'm trying to get away from that. Conversely, if the diagonal is closed, then if you suppose x is not equal to y for x, y, and x, then as the complement of that diagonal is open and xy is an element of that complement, we find that there exists an open u cross v in that complement with containing xy, which is a subset of it, right? But that means that x is an element of u and y is an element of v, and it also means that since this u cross v is a subset of the diagonal, that means that it's a sneaky way of encoding the non-intersection of u and v in this notation. If you don't believe it, just write it out, you'll see it. Therefore, we've separated points with open sets which are disjoint. It's Hausdorff. Woo-hoo. So there's that. Let's see here. 4. This is another corollary which is very useful. This is something that we need for applications all the time. So let f and g be continuous with y Hausdorff. The coincidence set, which is x and x such that f of x is equal to g of x, is closed in x. So consider the map f comma g from x to y cross y, defined by f comma g of x as f of x comma g of x, right? Sometimes this is called the Cartesian product of maps, all right? This map is continuous, all right? And the coincidence set is the inverse image of the diagonal under this continuous map, where and by the way, if you don't believe it's continuous, remember the previous theorem that, so like you could call this map H, and then like the first component of H is F, the second component of H is G. So we proved previously that if you have such a mapping, if the component functions are continuous, then the whole function is continuous. That's how I know that f comma g is continuous, by the previous lecture, by lecture 9, where we had the theorem for the continuity of mapping on the product in terms of its component functions. F and g are the component functions of this map, so it's continuous, and the inverse image under a continuous map of a closed set is closed. right? Because we know the diagonal is closed by the previous theorem. Hence, the coincidence set is closed. So that's pretty nice. That has applications to the theory of fixed points, among other things. So if you have a continuous map on X and you have an X for such that f of X is equal to X, it's called a fixed point. And so for Hausdorff, for X Hausdorff, the set of fixed points for a continuous map, I don't know why I say finite, dummy. Fix that before I scan it. Tomorrow probably. The school does have nice scanners, much better than my phone. So anyway, the set of fixed points for a continuous map is it's C, and I would just point out that it's basically, again, it's a coincidence set. F of X equals G of X, but here the G of X is actually the identity map, and I think we're also thinking of Y being equal to X in this context, so relative to the corollary. But in any event, it's a coincidence set, therefore it's closed, so the set of fixed points of a continuous map is closed. And then finally, we reach the final lemma of this lecture. And I tried to draw a picture on this page. We're going to have to go to the next page to do it justice, but let's try to start processing the proof here. So let X be Hausdorff, all right, with x1 through xn distinct points in X. Then there exist open sets u1 through un in X, such that, well, each open set contains the point xj, uj contains xj, all right, and the u sub I and u sub j are not equal. Excuse me, they're non-intersecting if I is not equal to j. Of course, if I equals to j, they're the same set. Any set intersect itself is the set again. All right, fine. So I started trying to draw a picture. Here's my endpoints: x1, x2, x3, xn minus 1, xn. And so Minetti starts looking at these u12, u21 sets, but and then he constructs the ui that you need for the lemma in terms of intersecting all the uij's for I not equal to j. And I started to see it here, but I think you'll see it better on my next page. All right, so I mean, Minetti doesn't have a picture, but that's all good. So here, let me let you stare at this here for a second while I go grab my colored pencil, because I want to try to shade in where the U1 is in my picture. All right, I forgot to bring my colored pencil. Let's see here. So what I attempted to do is to try to illustrate the proof for, like, you know, four points. So let me just try to trace it out and explain what's going on here. So for point 1, we can look at U12, and I did it in green. So like U12 is this guy. Wait, I lost track. Where's my U12? Okay, this guy. There's U12. And then this guy goes over here is U13. See, it encircles U13. And then there's U14, which comes over here like that. All right. Oh, I'm a dummy. Oh, rats. So still not quite right. I mean, U14 is the set which so curses. All right, well, man. All right, so U14 does not contain X4, right? It should have stopped. It should have stopped short. So U14 just contains X1, and U14 does not contain X4, and that's by the Hausdorff property. So I'll try to fix this here. It's gonna be a bit messy. Let's see if we can fix it. So what I should have done is something more like this. I don't know. Now it doesn't really see the thing, and I'm not quite doing it justice either, because the U. So I guess it was helpful to me to draw U14 over here just to emphasize its connection to X4. But the real connection to X4 is not that it contains X4; it's that it doesn't contain X4. See, so this U14 that I'm drawing, right? It could have contained everything else except for 4. So like, well, it's too late to fix that one for that, and I'm not sure I want to fix any of them like the one I'm thinking of. But let me just, so here, like U13, it can't contain 3, but what it could have done, perhaps would have been better, is if it could have been like this. It could have actually contained everything else. Let's see where that came from. Let me follow it back to the source. Oh no, I've lost track of it. Oh no. Ah. Fine, I give up. All right, let's try that again. All right. It's arts and crafts time. So here's your X1. Here's your X2. I think 3 will suffice for my picture here. I'm gonna just cut it back to 3. All right, so U12 could look like this. Okay, this could be U12 because it contains 1, but it doesn't contain 2. Now U21 could look like. So I'm going to make all the ones that are centered on U2 blue. Okay, so U21 could be something like this. All right, that would be U21. It cannot contain 1 is the point. All right. Then let's see here. I guess if I'm foolish, I can add a 4th point. I'm going to regret this. X4. So I can also talk about what I can also have a U13 like that. So the key is it doesn't contain 3, right? And then if I can talk about that, I can also have a U2 let's see here, U21, U24, I guess. Could be like this, right? No, it contains everything except for 4. And now I'm starting to regret adding that 4th point. Let's see here, so I have U21, U24 illustrated, and then I also have a U23 I need to draw. U23, it could be something simpler, right? U23 could look like this, okay? It doesn't have to contain everything. The point is it could contain everything except for X3 by construction. So the existence of these U2 sets is by the Hausdorff property of the space. All right, so there. I think I have I think I have at least an example of everything on the X2. I've got 2, 1, 2, 3, 2, 4. Right over here, I've got 1, 3. I got my 1, 2, and I should also do a 1, 4 map, a 1, 4 thing around that. to be complete. 1, 4 can contain whatever it wants except for 4, right? So it could be like that, for example. So there's U, 1, 4. All right, so you have n minus 1 of these sets containing the particular points involved, and then what he does is he just forms the intersection, right? He defines the intersection ui. He says it's equal to the intersection over I not equal to j of uij. Right, so like, for example, u1 would be u12 intersect u13 intersect u14 in my example here, right? Or u2, let me do the 2 in blue, 2 in blue. u2 would be my u21 intersect u23 intersect u24. Fine. And then, so that intersection I think I could illustrate. So the blue doesn't count. I'm only looking for u1, I'm only looking inside the green. So I think, if I'm not wrong, it would just be like this. So I'm looking to be inside the green circles. I'm sure you could think of a better way to illustrate this than I have. And let's see here, and then inside the blue circles, containing all the blue circles, not circles, but the blue sets, right? Containing the x2, you see that there's, a common intersection to all of those, which is close to, it contains x2, right? Because they all contain x2. And since we're intersecting, in this case, 3 open sets, we get an open set. And of course, by construction, u1, well, fine. By construction, this u1 here, right? And then this u2 over here are disjoint, right? So anyway, that's the idea of the proof, dragged out with an unnecessary drawing, but there you go. Anyway, so that's what we have to say about Hausdorff spaces today. And Hausdorff is something that will come up again, I'm sure. So anyway, thanks guys.